So here we go, Mathematica. Mathematica is another interpreted language, so if you want to do anything, you need to have it. That's why I'm giving you all these licenses. By the way, it should be 9 of you people should still be missing the license. Everybody else should have it. And I talked to Wolfram today. They're switching the licenses, so a couple of days and I think everybody will get it. Contrary to MATLAB, this is the console, and most likely you will be editing and writing your programs inside the console. So normally I say you use your own editor and then you execute your scripts from the console. Well, in Mathematica, actually, you edit, you do everything inside the console. So this is it. When you type something, okay, first of all, since we will be doing all the editing in here, I like to select something a little bit more appealing. So I like the standard report, gives me some colors, and then we need to magnify this thing. Okay, maybe that's too much. Okay, so the moment you type something, over here on the right, a cell pops up. What does that mean? It means that whatever you're typing now is contained into this object called cell. And whenever you want Mathematica to perform some computation, some evaluation, whatever, you have to evaluate the cell. So you would be selecting the cell, or as long as you're inside the cell, that's fine. Now you have to do Shift-Enter together, and the cell is being evaluated, and the result of the evaluation is displayed into another cell. This is the input cell, and it's numbered, input number 1. This is the corresponding output cell, and it's numbered. And then both of them are grouped together into a bigger cell. You can actually close and open cells. When we have maybe 10, 20 of them, you can group all of them and then you can close or expand them. This is useful for presentations and also for programs. I'll show you a little bit later. You can have different types of cells. For instance, you can put some comments. As it is, this is an input cell, so that's not very nice. Then you can change it into different styles. You can put more importance, and so on, whatever. So now this is a text cell, and what that means is that you cannot evaluate it. Even if you press Shift-Enter on this cell, nothing happens. In fact, the enter happened. On the other side, this is now, see that we lost the input because this now doesn't correspond to input 1 anymore. I changed it. And now if I want to evaluate it, Shift-Enter, and I get output number 2. Input and output number 1 are not lost. It's just that they are not displayed anymore. If I type out 1, I get the result, the earlier result. All right, and now you see that we have 3 groups of cells, and there is a big cell that contains everything. So that's what I was saying. I can group them, I can close them, I can collapsing them, I can expand them, and so on. And this is important when you write programs so that you can have a nested hierarchical structure, and you can collapse and expand whatever you want. All right, so much for the beginning. Just to give you an idea, Mathematica was inspired by Lisp, and as such will contain lots and lots of parentheses. In fact, Mathematica uses standard parentheses for precedence orders, square brackets, function calls, double square brackets to access a list, curly brackets or braces to create a list, and then that thing are comments. So if you execute these things, you see it's actually grayed out. It's very nice. Okay, just to have an idea of what the syntax will look like. Also, Mathematica is a functional language. Again, it's inspired by Lisp, but it has evolved into a general purpose, general programming language that contains constructs like the while loop, the for loop, that have absolutely nothing to do with the functional language. It has also all sorts of assignments, exactly like in a functional procedural language. So by now, you can program any way you want. You don't have to stick to the functional style. But that's the one that I will use the most. And in fact, if you use for loops and while loops, you'll piss me off, and your grade will go down. So, you know. As I said, as I introduced MATLAB, the most important thing to learn at the beginning is how to get some help. And in Mathematica, you get help with the question mark. So question mark by itself, if you evaluate it, it tells you that if you attach a name next to question mark, then Mathematica will give you some information about name. So let's say that we don't know how to use plot. Then I say, what is plot? And it gives me a very, very brief idea of what plot is. In fact, for the most part, it just gives me the prototype, so that maybe if I don't remember the argument list, okay, that's a reminder. But then there is this link over here, and that, if you click on it, that takes you to the help browser. And truth to be told, the help browser used to be a really, really good tool, and from version 5 on, I think, I don't like it anymore. Still, it's, if it's a one specific function that you want to learn, then it's perfect, because it gives you the argument list over here. Let me magnify a little. Argument list. Into more information, it goes into a pretty detailed explanation of all the options of each function. And then it's nice because there are these sections down here with examples and all sorts of things. So if it's one particular function that you want to learn about, the browser is pretty good. If you're completely lost, then the browser is probably not the good place to start. Probably it's good to go here at the very beginning and then try to work your way through, starting if you want graphics, okay, if you want programming, is somewhere else, and so on, and so on. The question mark does much more than that. In fact, you can use wildcards, and wildcards are very useful. For instance, if I know that Mathematica can do something, or maybe I suspect that it can do something, but I'm not sure what the function is called, I can put a wildcard there, and now all the plot functions will be returned. Actually, all the functions that start with plot. Maybe I know that there are even more. Exactly. Now I catch list plot 3D, and all those functions that, you know, wildcards. So this is very good. Yes? Okay. And for you to know every single function that is internal to Mathematica as a capital letter. So it's good habit when you program, when you define your own function, to start with a lower letter, so that you distinguish what's defined in Mathematica and what is yours. You don't have to, but it's a good habit. And also, when there are multiple words, when a function is composed by multiple words, each word is capitalized. So that's a good way of remembering, and also, just by trying out, you can find functions like that. As a reference, as I said, the browser is a good start. There is no Mathematica Book anymore. There used to be in the earlier versions. Now it would be something like this, so they stopped printing it. But if you go back, maybe in the library, and you find the Mathematica version 2 or Mathematica version 3 manual, that's a pretty good starting point. It gives you a very good idea of how to program and what functionalities are offered. Okay, so that was to start. Now let's see what Mathematica does. Mathematica, it's a very powerful calculator. So it can do stuff like this. So it knows the standard operations. You can do stuff like this. Now you see that immediately we go into a realm that we were not used to. We have a really long number, and Mathematica tells you every single digit of it. If you think that that's not long enough, we can go to something much longer. Okay? Of course, maybe you have no idea what the value of this thing is. Then you can use the function n. The function n tries, and for the most part successfully, so transforms any number or any symbol or any expression into a measurable number. So if we say n of 3 to the now we have a nice exponent, and we have some 16 digits here. And so we have a better estimate of how large this number is. Let me tell you right away. So that for style reasons, it's good if you change this setting of Mathematica. By default, Mathematica tries to display only 5 or 6 digits in a number, and to me that's really annoying because you think that that's all he knows about a number. So by default, over here you would have maybe a 6 or a 5, and what that means is that if you if you compute this thing here, it only has 6 digits, okay? And to me, these digits are too few to believe that that's an approximated number, so I much rather set this to 16. Now this gives me a better idea. It's something that you have to go into the preferences and change yourself. There are ways of doing this number by number, cell by cell, but I think it will be better for you if you just set it once and for all. Okay. Now let's look at some arithmetic. I said it's a very powerful calculator. It knows a lot of mathematical functions. That's factorial, of course, and it computes the factorial exactly. Now we can do stuff like this. What will be the answer? Yes. And when you say square root of 3, do you really mean square root of 3 like this? So it's left unevaluated. It is a square root of 3. It realizes that if it converted the square root of 3 into a number, it would commit an error. It would become an approximation. So since we started from integers, and we're doing nothing else but just elevating to the power of 1/2, it says, let me leave the number as it is. And that's why I say that the function n takes an expression and tries to spit out a number out of it. If you put an n, function n, evaluated on that, then you get an actual numerical value. So let's say here we go. Of course, it's not the same as before. Well, this is it. No, I was correct. Yes, I was correct. Okay. So Mathematica similarly leaves everything unevaluated as much as possible. This computation here only involves integers, so the computation, the result will be a ratio. It will not be 1.333 or whatever. The moment you insert a real number, things change dramatically. Where is the big difference? Well, 1.5, it's not an integer anymore. So immediately we go into the floating point arithmetic realm. And so everything else is converted in a floating point arithmetic, and the result is a floating point number with 16 digits. This is a symbol. Okay, and you're not going to get anything out of it. Opposite to MATLAB, in MATLAB you will get a number. Over here you simply get pi, and if I say pi over 2, I still get pi over 2. And if I ask for the square root, I get the square root, and so on and so forth. You don't get anything out of this. Why? Because Mathematica says we're starting from exact numbers. Everything else is just a function of this number, so why should I make a mistake? It says let's keep everything unevaluated and let's carry on this number exactly, symbolically, as much as possible. The moment you want to look at this number, either you put a dot there. This changes everything, because now we don't have integers anymore. Now we have a floating point number, and so here we go. Or we compute the n. Okay? N stands for numerical, of course. So n does more than that. N of pi is pi. But remember, in Mathematica, pi is a symbol, yes, but it's not a constant. It's a concept. There is an algorithm associated to pi. So if I ask for the first 100 digits of pi, I will get them. It's not that this is stored somewhere and I'm accessing the first 100 digits. When I evaluate it, I run an algorithm for computing the first 100 digits. And I can go on and compute the first 1,000 digits and so on and so forth. Okay? Same story for other numbers like e.
Isn't it a bit fast calculation for digits?
Oh, there are I think cubic algorithms for computing these things, so this is no problem. No, I think even more than cubic. If you have a constant, you can speed this computation like crazy. Yeah. Okay, next. A, we have not assigned any value to A. We have not declared the variable A. So if I type A and I try to evaluate it, what will happen? So the suggestion is it will treat A as a symbol. That's a very good guess. There is no mistake made. A, we don't know what it is. Okay, that's fine. Let's just keep it as a symbol. At this point, if I say A plus A, 2a, perfectly. It's just an algebra of symbols. It's no problem whatsoever. And I can do a to the power of b, and it stays unevaluated. And no, to the pi, sure, that's no problem. A plus a, oh, I had a nice one. Okay. Yes.
So now if you do n numerical cases, will there be an error?
No, of course not. So you're saying if we put, what would you like?
N outside and square bracket, like we do for numerics.
The only difference is that now the 1 has a dot. It has been transformed into floating point 1.
How about e to the power of I times p? So why does it show -1 plus b and not -1?
That's how it orders the variables. It normally orders them with numbers first, and then all the variables in alphabetical order. Okay? Actually, what you were asking for is probably e to the minus I pi. Two. No. Ah, thank you. Thank you. Yeah. That's what we were looking for. In fact, oh, totally forgot. Eventually it would arrive. So, function can be invoked by prefix notation, like any function, or by postfix notation with the double slash. I will get there, but for sure I will use this a lot. So every time there is some computation and then you think of some sort of a post-processing step, it just comes very natural to say, okay, this is all the computation I want, and then let me post-process with this function. Then you say double slash n, and you can pipe multiple post-processing functions. All right, so what do you say? Notice I used the double equal, which is the question mark equal. I am comparing to. What do you say? True? Any other take? We have a true. False. Okay, so it says true. That was unexpected. Okay. Sorry guys. So let me try this one. Yes. So, yeah, sorry. 2 equals compares the values. 3 equals actually compares even the types. Okay? All right. Notice that the first one is an integer expression, and these other 3 guys are all in floating point arithmetic. Okay. Something more. Let's say that I take pi squared, first 30 digits. Okay. I didn't assign this number to anything. I have not shown you an assignment yet. Still, I can recover it with the ampersand. That means the last result, the last output. So if I say that minus 9, or maybe I say abs that minus pi squared divided by pi squared. Basically, I'm asking how far away we are from pi squared. Here we go. So this object here takes the previous result, and then we do some math. And what I see is that I have an object which is accurate for 30 digits. This is no surprise because I asked the n to compute 30 digits of pi. Notice that this pi has infinite precision, so I can compare these objects, and the remainder, the relative error, is of the order of 10 to the minus 30. So I can do double thingy there, ampersand, and I go back 2 times. So I'm still referring to the pi square, and I can nest these things, and so I go back any number of times. Again, this is the same as output 48. Okay. What else?
One question.
Yes, please.
Does this count really the output or the cells before? Is it 2 cells before or 2 outputs before?
This is the output before. This is the 2 out. I mean, the last but one output, and so on.
But it doesn't work on cells, but
No, not on the cells. You can go anywhere, and you can add it anywhere you want. Okay. In fact, you can go inside an old cell and modify it, evaluate it. I showed you that already. And also nowadays you can even go inside an output cell, and the moment you do something, immediately gets turned into an input cell, basically so that you can use the output immediately. Here we go. Okay, so far so good. So I created a primer. Everything that I have mentioned so far is in the top cell over here. I try to explain how to execute and whatever. Now let's get to some computer sciencey thing. Let's look at some assignments. Okay, comments. I showed you this already. It's not going to be evaluated. Notice that this is a big cell, and I've put multiple instructions, multiple commands. As in MATLAB, the semicolon inhibits the output. So this is effectively a list of statements. They will be executed one after another. Maybe I can come here and show you. If I say c equal 3, even though this is an assignment, it's also a function, and the function returns the value of the assignment. That's why the output cell contains number 3. If I do this thing, if I put a semicolon, the assignment is performed, but there will be no output. Okay, and now I can do d equal 1 or pi. This will be a sequence. Actually, let's do c plus pi. This is a sequence of assignment. So first the c will take the value of 0, and then d will take 0 plus pi, or 1 plus pi. If I ask now what is d, it tells me 1 plus pi. Notice that it's been unevaluated. It was unevaluated. I can ask what c and d are now, because I have defined them. C, it's a global variable, and value is 1, and d, same story. In principle, now here it makes no difference, but you can ask a double question mark, and you get more information about the functions. For instance, for plot, this only tells you, as I said, a little bit a shortcut. on the prototype. This also gives you the options and the attributes. And as you can see, plot has tons of options. Okay, now, a number of different types. A equal 4, A will become an integer variable. B will be a complex number. Why? Because I have a square root of a negative number. C will be a string. D is a function call. Notice that we have not defined function yet. This is a symbol, and F is a list. Notice the curly braces, they construct lists, as I told you already. So if I evaluate this thing, I apologize for the alignment, but it's horrible. Look at that. Terrible, terrible. Okay, if I evaluate this, do you see any problem? There should be, yeah?
Well, function D might be interesting.
What else? Yeah, D might be interesting. Will we get an error, or what will we get?
Maybe it's just another type. Just as pi as a symbol.
Let me evaluate. See that everything was commented. I didn't get any warning, any error, nothing. Simply D from now on is a function of 4. It's no problem whatsoever. D is function of 4. The fact that function is undefined doesn't bother Mathematica at all. We know that if at some point function will be defined, okay, good, the D will be function of 4. Otherwise, it's just function of 4. So it's not that easy to make mistakes in a way. It's not that easy to get a mistake out of Mathematica. Clear is a function that takes one or more variables and removes them from any definition. Okay, here I'm assigning a plus 3 to x. I didn't have a semicolon, so I get 3 plus a. If I ask what is x, it tells me, oh, it's a global variable, it contains 3 plus a. Okay, now I define b as a constant pi over e. And I want to show you that Mathematica has two different types of assignment. The assignment that I just showed you, and the delayed assignment, which is colon equals. So let's see what the difference is. I define both y and z to be e times b. B is pi over e, so both y and z should probably be, answer, what do you expect y and z to contain now?
The same.
Yes, and the same and? Pi. Okay, let's see. Yes, both of them spit out pi. Now I reassign b. B initially was pi over here. Now I say b, it's only e. And I look again at the contents of y and z. And now something has happened. Y stayed the same, nothing changed, but z has been re-evaluated to e squared. Can anyone understand why?
Because of the delayed assignment.
Precisely because of the delayed assignment. So, y was evaluated once and for all. The right-hand side was evaluated. The value e times b gave pi. Okay, y now has a big error that points to a cell of memory, and this is a cell of memory, there is the value pi. That's it. Z is actually more, is something that looks more like a function than a constant. Z will be re-evaluated every time we ask for z. In that particular case, we know that z equals e times b. But that e times b has been assigned as an expression. There will not be a cell of memory with a specific value. Now it's more of a function. And every time I look at z, in reality, I have to look at what E is, what B is, and then I multiply them together. In the second case, my B has become E, so then z evaluates to E squared. And by the way, in Mathematica, I cannot do stuff like this. I cannot reassign constants. So even though this tells me the result is pi, E is still E. Okay? So see, here it says symbol E is protected. Many of the one symbol, one capital letter, symbols, whatever, are taken. So E is taken, D is taken, this is the derivative, I is taken, this is the imaginary unit, and there are more. I think Z is taken as a function, and so on. Okay, moral of the story. The assignment should be used to assign constants or independent variables. The delayed assignment really should be used for functions. If we look at what y and z look like, now we clearly understand the difference. Y is the number pi, no matter what the rest of the word tells us. Z is still unevaluated, and it will be constant E times B. So depending on the value B, Z will change its value. This thing here, don't look at it until we have done the next section. So now we get into the next section. Replacement rules. Let's clear everything. We start from x equals 3a. Since we will use this a lot, let me write it down. Think about this a lot, okay? We will do a lot of... Okay, question, what is x? Oh, we know, it's 3 plus a. And now I introduce a little bit of syntax. Slash dot means that I want to apply a replacement rule to my expression. So I will have expression, slash dot, and then a replacement rule. What is a replacement rule? I say expression 1 will be substituted, replaced by expression 2. This arrow is composed by a dash and then a greater than. So here is a replacement rule. I say, please take x and apply whatever replacement rule comes next. The replacement rule is a turns into a 5. So what does this evaluate to? We have a vote for 8. Let's see if we get to 8. We have the a is turned into a 5, so the result is 3 plus 5, 8. Notice, important, that x has not been assigned. X is still 3 plus a. Okay? I have performed the replacement of the value of x, but I didn't assign this result to anything. What is this? What do you think? Oh, this is just me. Since I easily get confused with operators, I like to put curly braces just to have a better idea of, just to identify the replacement rule clearly. You don't have to. This is just for me, okay? So over here I say expression is x, and I want to replace 3 with a, if this is possible. So do you think this is possible? What do you think we get out of this?
2a.
Somebody says 2a, okay. Is anybody concerned that I am replacing a number for a symbol? Nobody? All right, you guys are smart. It gets to 2a. Once again, if I look at x, no value is stored. Okay. What do you think this is?
X divided by 0.3.
Any other take? That's not quite the right answer.
This is A. 11.
This is A.
Yeah.
This is not A.
I think there will be no change.
Okay. Notice that this is now a division. Okay? So what this is, it's just a replacement rule. This is an expression on the left, and it will be replaced by A. So the whole thing is just a replacement rule. Whatever is on the left should become an A. I don't apply this rule, it's just a rule. Okay, more replacement. Next one is a bad idea. X is already assigned to something, yet I come up with this stupid idea of replacing it with -10. What do you think will come out of this? I want to show you this because this is something that you guys should not do. So let's just go through this once, and then I hope I convince you that it's not a good idea to program like this. So x was assigned to a value, and now all of a sudden I decide to replace x with something else. What do you think I should get out of that?
So actually it's like trying to change k to -13.
-30. I honestly don't.
-13.
Oh, 13. Okay. So let me do something. If we are in the memory world, we said that somebody in the memory, here there is x, no, a plus 3. Okay, and now I'm asking Mathematica to take this and replace it with -10. You guys look confused. Well, a possibility would be nothing happens. I'm trying to replace 3 plus a with -10, so nothing happens, right? Is this replacement rule so obscure for you guys? Yeah?
Trying to replace something on the left side. The left side is x,
Mm-hmm.
and so I'm replacing x by -10.
Okay, so let's see if that's what happens. It's exactly what happens. So Mathematica, this is not really just an arrow, it's really a double arrow. And it says, yes, a plus 3, it's actually x, so I'm trying to replace, and so it says, oh, I find it, and it spits out -10. Okay, so far so good. Now look at the next one. X plus 10, what do you think this is? X plus 10, this is kind of easy, right? Should be, oops, should be 0, right? And that's the nasty thing. So now we are doing some math first. And the math we do with the value of x. So we have added the 10. Now it's 13 plus a. Now I ask for a replacement. Oh, okay, where am I? Now I'm on this side, and so we get something unexpected. So this is clearly a bad idea. Once you have assigned something, you cannot use the you should not use the left-hand side as a replacement term. Yes?
Does replacement apply only to 10 or to x plus 10?
No. The replacement applies to the whole thing. It's it's like this. That's the precedence order. So what screwed up our prediction is that since we do some math, we're not on the left-hand side anymore. We are working on the value of x. And at that point, we have lost this connection here. I ask for a replacement. We don't have x anymore, so we have 13 plus a, and that's it. So there is no change in the replacement. Okay, back here, we have a and x. We want, okay, what do you think that tells us? First of all, what is a? A is just a, okay? And now I'm saying replace x with 5. Okay, nothing happens. Come on, guys. Don't be scared. So 3 plus a, and I replace x with 10. Same story, right? Nothing happens. Oops! Look at that. 3 plus a. Oh, look at that. It's here in the memory. Didn't we say that there is a double arrow? So now we're here, and now all of a sudden goes to 10. Guys, this is really awful. So if x has been assigned, don't use replacement rules like this. Otherwise, you'll get in a complete mess. We can do this. Okay, how about this? This is kind of intuitive at this point. X, we know that x is 3 plus a. We take 3 plus a, we replace it with 10, so it should be 10. Yeah. So that is fine. We are working in the memory side. We take this object, we replace it with 10. Okay, that's what we expect. Enough for this. I think I made my point clear. Don't use replacement rules like that. Back to meaningful examples. X. So x, we are back here. X is 3 plus a. And I am replacing a with x. What's the output? So I'm not trying to trick you. This is all predictable, and that's the way of actually performing these replacement rules. So what do you think the output is? False. False? Who said false? How do we get the Boolean?
Since it's x equals 3 plus x, it's not possible that...
Whoa. This is not an equation. It's not a double equal. It's one equal. Means that x has been assigned by 3 plus a. Okay? It's not a double equal. Somebody else was saying? Somebody says 3 plus x. So let's vote. Here. Possible answers. We have false. Not making fun of you, but okay, it's not false. Then we have a 3 plus x. That's a possibility. What else? Let me push this a little bit higher. Okay. Any other take? Any other opinion? Guys, we know that x is 3 plus a, okay? And instead of a, we are putting 3 plus a. So how about 6 plus a? So 6 plus a, Paolo is smart. He's the only one who guessed it. Okay, there is a way of adding more than one replacement rule. Let's say that you have replacement rules for more than one variable. So if you have more replacement rules, the precedence is from left to right. First of all, x plus y, where a goes to y. So x plus y, now we have 3 plus a plus y. That's on the left-hand side. And we replace a by y. So what will we get?
3 plus 2y.
Sounds reasonable. 3 plus 2y. Okay. But now I ask, a goes into y and y goes into 4. 7 plus 2y. Any other take? Everybody agrees with that? No other? Ah, sorry. 7 plus y. Nobody complained.
Is the replacement? Okay, no, that's okay. 11.
Okay. Finally, we get some debate. Okay, what is the rationale behind 11? You guys are saying a goes into y, so it would be 3 plus 2y. Then y goes into 4, so 3 plus 4 plus 4, 11. Nope. Because the rules are applied only once. For now. Then there is another command for applying rules multiple times. So what we're doing is this object here, which is called also what is it called? Replacement? Replace. Okay? And I'll show you later what the other one is. So first let's look at this other example. Same situation. Now y goes into 4, a goes into y. Yeah, it's the same. I just reversed the order, but the match of the variables is separate. One operates on the x, one operates on the y. They don't affect each other, so the result is the same. Now things start to become interesting when I apply the double slash dot, which is the repeated replacement. Here we go, and it's called, I think it's called replace repeated. Repeated. Okay. So what happens now? Now it should be 11, right? Now we keep applying these objects. We keep applying these rules until the left-hand side doesn't change anymore. So now we go to 11. When we are at 11, I certainly don't have an A, I certainly don't have a Y, so I stop my evaluation. What about here? 3 plus y plus a. A goes y, y goes in a, so we swap, we switch the values. So nothing happens. But what about the next one? What about this one? Sorry? So you're saying that we enter an infinite loop. So let's go. We have We have an infinite loop. Other suggestion?
So nothing happens.
So nothing happens.
G plus A plus B.
And we report them in like an error.
No other take? What's the semantics? I told you these the rules keep getting applied until the left-hand side doesn't change anymore. Well, the left-hand side doesn't change immediately. You have x plus y, you apply the rules once, you end up in x plus y, that's it. But this one now gets more interesting. How about this one? What's happening? Okay, the a becomes y, the y becomes 2a. That's the first iteration. Then 2a becomes 2y, y becomes 2a. Then 2a will become 2y, and this y will become 4a, and so on. So this thing actually will not terminate. This was a long computation. It went through 65,000 iterations, at which point it decided that probably there was something wrong. Probably we didn't mean to go into such a long loop, and it said, okay, that's enough. In case we really wanted to go through 65,000 iterations, maybe we wanted 66,000. Let me just show you how this thing could be done. So if we look at replace repeated, there is an option that says max iterations 65,000. Okay, there is a function that says set options, not that you will never need it, but then you could change max iteration to anything you want. Maybe you want to set it to 16, so that maybe if something goes wrong, it's more manageable. Or maybe you really know what is going on, and you know that your object is 100,000 levels deep, so you need to increase that. Okay, I don't know why this was here. Okay, more replacements. I know why this is here. To help you guys in looking at this one. But I plotted it, I've drawn it in on the board. Okay, now we have a two-stage replacement. We start from x plus y, and we have a first replacement rule, and then we have a second replacement rule. Let me write it down. So you're saying 3 plus a plus y, 3 plus 2a. I see people nodding. So the first replacement turns the a into y. So we have 3 plus 2y, and then y becomes a, so 3 plus 2a. Okay, I like that, thank you. And what I'm showing you here is the exact same replacement rule, just in linear, let's say, in compact mode. So if you use the semicolon, you can nest two replacement rules one after another. Notice that this is entirely different from this one, okay? Completely different. The next one is a list of different replacement rules. So I have replacements, okay, and I have a list, and inside the list, I have two separate replacement rules. So the result will be a list, will be the left-hand side, one when the left replacement rule has been applied, and one where the right replacement rule has been applied. Okay? So this is just syntax for you guys to be able to use the replacement rules. So let me clean. And now we do some examples. Why on earth would I ever use replacement rules? Normally, you will have a list, complicated or easy list, long, multi-dimensional, multi-level, and maybe you want to do some filtering, or you want to apply some operations, some analysis, whatever. For instance, I have this list with a lot of A's, and now I want to specify one value of A. I know that now A is Z, okay? So I do that, and all of a sudden my list becomes expressed in terms of Z. There is no A anymore. Maybe I know that A has to become 4. Okay, now I have specific values. So over here, I could put functions, and then I could evaluate the functions just with the replacement rule. But this is the best part. So this is your first encounter with a pattern. You should remember this moment like your first date. Oh my God, this is when I first met a pattern. How beautiful. That's the underscore. This object here is called pattern. Maybe you're not going to fall in love at first sight with a pattern, but I promise after 2 or 3 lectures you will be deeply in love with these objects. Okay? So what is this pattern telling me? It says every time there is A raised to whatever, this means whatever. It means to anything, okay? Whenever A is raised to any power, turn that whole thing into infinity. This is just me being funny. The important thing comes here. This object here is a pattern. So now Mathematica will apply the replacement rule to all the objects that look like A to the power of anything. So, what do you think the result will be?
3a infinity, 3 to the power of a infinity, a infinity.
So it looks like we will have a couple of infinities around. And that's exactly right. 3a doesn't have the structure of a to the power of anything. A, yes, it is, so we turn it into infinity. 3 to the power of a doesn't look like a to the power. A to the power, okay, good, and a. Yes, question?
Well, what with our experiment, the star, the little star you use with plot?
I didn't understand anything. Say it again.
You use the star when you plotting, when making
Yeah.
star plot.
Wildcard.
Isn't that something?
Sure, but wait a second, because this pattern has a lot of secrets. The star is just a star, it's a wildcard. You substitute it with anything. The pattern is absolutely beautiful, and you have to know it slowly. You cannot just get to, no, there is much more to it. So just wait. We can spend a few lectures on patterns. Here is another pattern. What do we do here? How many infinities do we get? So you guys realize now that this object that was not matched before now is matched because it's a power, and I'm trying to match powers. Okay. And that's exactly what happens. 3 infinities. What happens here?
Nothing actually.
Nothing? Yeah?
I match the x command to x,
Yeah?
and then replace x with a.
Okay. So read the output.
Ba to the power of a, no, yes, 3 to the power of a to the power of a factor.
Okay, you know patterns already. So he noticed already, here is, you don't do this with a wildcard. So now I assigned the name to the pattern. I said, every time we have a to the power of something, that something, I call it x. So not only it matches, but I assigned a name so that I can use it on the right-hand side, on the right part of the replacement rule, I can refer to whatever object is here by x. Why is this beautiful? Okay. This is fine. In this particular case, x was matched with 2, and so these two guys have been flipped. Okay, next one. And the next one, now I can switch anything, obviously, and what I wanted to show you is that over here I can put a plus b. Okay? So it's not just a character, now I have matched the whole expression. This a down here matched this whole thing, and since it was raised to the power of a, here I assign the base of the power to the letter a, I assign the exponent to x, and here I flip everything.
Excuse me.
Yes?
And instead of x, they can be also, for example, 2 plus 3.
No. Over here?
Yeah.
No. These can only be a symbol or, well, I can call it
Can you use some kind of regular expression?
exp. I cannot put an expression to be evaluated. It's only a noun, an identifier.
What I mean is, for example, in the left side, if a power 2 plus 3
A to the power of, oh yeah, sure,
match.
sure. Yep. Oh, absolutely, yes. I had a question somewhere? No?
What if I only wanted to match, say, to the power of 3, 7, and 11? Can I use regular expressions or something?
Yeah, you can put alternatives, yes. And for the alternatives, you put the pipe. Yes. Okay, this is just a very quick, short introduction to patterns and replacement rules. We will see plenty of these later on. It's just that I didn't want to overload you guys with this. So let's get into lists for 10 minutes, and then we call it a day. I told you already how to create lists with the curly braces. Here is a list that contains a little bit of everything. Contains some variables, some numbers, some symbols, contains the empty entry, contains the empty list, and some floating point number. There are ways of visualizing lists, so column form, column, full form. Full form is very general. It's used to see how Mathematica represents internally objects. So here is our replacement rule. What will happen what will happen? On the left, we have an expression, L. L is all that monster up there. And what I'm asking Mathematica to do is to take a list and replace it with plus. Precisely. I will not have a list anymore. I will have a mass, but that's okay. I'm asking to add all of those objects. So null stays as it is. The empty list actually disappears, and everything else is added together. Why does the empty list disappear? Not quite.
Because it is changed by plus.
Yes, because it's not going to be a list anymore. It's going to be a plus. It will be plus of nothing, so it just disappears. Tree form is pretty useful. It's a fancy way of visualizing the objects of different levels. If we add something inside this list, there would be further levels. Okay, let me show you how to access these objects. So L, this is the whole list. Okay, L of all. This is copying the MATLAB notation. It's the whole list. L, the indexing starts from 1, okay? So L of 1 is the first element, so it will be A. Same notation, this is a little bit more functional, coming from Lisp, car, CDR. First is the first entry. Here we go, L of 0. I told you it's not that easy to get an error from Mathematica. L of 0 is perfectly defined. We just have to go here. L of 0 is the head of the list. So it will be this object here, before the first entry, okay? So if I go down and I ask for L of 0, we will get list.
What about -1?
We will get there pretty soon. Rest of L is anything but the first entry. Again, if you know Lisp, this is a CDR, it's exactly Lisp. It's just called differently, but it's the exact same concept. So everything except for the first entry. -1, we count backwards, so it's the last entry. It's not a problem. -2 would be the empty list, okay? It's really difficult to get an error. Last is again the last entry. L of length of L. So length is a function that returns the length. So once again, this is the last entry. Now let's build some functions. Table, very, very, very important and useful. Table takes some expression and it evaluates this expression as many times as the iterator here tells it. So we have to understand what iterators are like. If you only have one number in braces, it means repeat it 9 times, repeat it. And so we simply get this expression repeated 9 times. Notice that we didn't assign this list, okay? So it's lost. Except for output, for out, except for this thingy. But now I use the iterator with 2 values. Now I put the name of a variable and I put a range. Okay, since I have a variable name, now I can use it on my expression field. So this will create a table evaluating square root of I, where I assumes all the values from 1 to 10. Notice that since we're talking about integers, the square roots will be not evaluated, except for where the square root is an exact number. Now we have an iterator with 3 indices, so I from 5 to 10, steps of 1. Okay. Now we have 4 arguments here, so now we go backwards. This is the step size. Here we go. So far so good, I hope. Yeah. Nobody's freaking out. Okay, this is a different way of using lists. This is the expression that I will build, the function that I will evaluate. I specify the variable number, and as my right-hand side, I actually enumerate all the possible entries. And what do I say? I say that there will be a T, an H, an E, S, E, an empty, blah, blah, blah. Okay. When I evaluate these, we get a list that says that these are 12 entries. So I squared all of these entries. This was a square root, so it becomes 12. Anything else was a symbol or an empty thing or a string, whatever. So I squared everything. Notice that there is no mistake. I get no complaints, no warnings. So all of these are different types of iterators. Just a number, so we repeat 9 times. 2, 3, 4 arguments. Over here I get the full list enumeration. Okay. We don't have to work with integers, of course. So now we go from pi over 3 to square root of pi in steps of whatever that is. And I get a bunch of floating point numbers. Okay, what's next? Here I build a list. So we go from 5 to 14 in steps of 2, and then I don't really care about the list itself. I ask for the length. Again, it's a kind of a post-processing, so I put / function. And what I care about is simply how many entries were created. Random numbers, I can use random integer like this. So this one is a number, spits out a number in the range 1 to 10, and I ask for 6 such numbers. A shortcut for the same is please create me a random integer between 1 and 10 and create 6 of them.
Spit out a 0, so it's from 0 to 9 probably.
Thank you. It might very well be the case. Why don't we look up? Zero Imax. Okay. So yes, it includes 0. And Imax is also included. So it will be from 0 to 10. That's okay. Over here, I evaluate this function where notice that I is not the capital I, so this is a variable. Be careful to these little things. This is a something. This is a something else. Okay, be careful. Same story as before. What do you think the output is going to be here? Yeah. So I will evaluate this expression, some f of pi, where f will assume all of these numbers. So this will be sine of pi, cosine of pi, exp of pi, some unknown function g of pi. This is a pure function. I will explain next time what a pure function is. But we get 0 minus 1 e g. We never define g, as I said, no problem. The last one is the square function. Okay, let's just finish with these 2 more commands. Range creates a range of numbers. You can also specify the step size. And finally, array, it evaluates a function in a range of values. So from g to so GT1 to G2 of 6. And you can find all of these, of course. Range, you can use it in multiple ways, and array also you can use in many different ways. Questions? Then I will see you on Thursdays.